Okay, good morning everyone. This is week 14. Well, I don't know if you've noticed, we have only 2 weeks left for the end of the semester. Okay, and this is episode 25. We have probably just 4 more episodes before the final exam. All right. And what's due this week is quiz 26 to 28 and Lala's PA. I don't know if you have started it. I've seen a couple teams that have already submitted a PA9, so that's great. So the topic for today, we actually talked about SDN's forwarding already last week, and we'll just finish SDN forwarding. Okay. And then we'll work on the quiz real quick. This one is very simple. And then we'll start routing. That is chapter 5. That is actually the intelligent part of the network layer. Okay. Hope that you are, excited as much as Polly does. With the generalized forwarding explained, now let's go back to this notion, the flow table. This is one of the most important things in SDN's data plane. Recall early slide. Flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column priority, okay, and we just ignore that here as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters we know, one counting bytes and one counting packets. Action column, 4 classes of actions. One can forward the packet to an outgoing interface. One can forward the packet to the remote controller. One can drop a packet as an action. One can also change the content of the packet as an action as well. So, all these straightforward. Now, this column here, very complex. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, in the early slide is also called a header column. The reason it's called a header column is we're using the header fields essentially to compose these rules. In the 3 examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. One can use other fields in the network layer header for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets coming into the router through a particular incoming port. So that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. So that's also why in this slide we refrain from calling this column the header column, because we do have a field that's not necessarily a packet header. So we call them rules in general. Let's take a look at how diverse these rules can be. Again, through a number of examples. First is the destination-based forwarding. Now, this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8. Now we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. The second and the third example are there to serve security purpose to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet definitely, okay, something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? Admin or root username and guessing the passwords for the root or admin. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. Okay? So blocking packets to port 22 is to block any logging request to port 22. Therefore, SSH is disabled on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack. DOS attack, denial of service attack. You see, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share IP addresses of zombie machines. So if one day a hacker hacks through the workstation, and take over the workstation, 140.112.42.161 is going to be a zombie IP address. So the experienced system admin, after looking up the website displaying all these zombie IP addresses, can set up these entries with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in, and asks all the zombie machines to issue, for example, login requests, then our machine is going to under attack. So experienced admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH brute force attack. Guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So for this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch, or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch will need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. So that is the use of the switch there. So you see why. This entry here is looking at the destination address at the link layer. That is also called the MAC address, and it looks very different from the IP address. So if this packet comes in matching this link layer address, that's forwarded to output port 3. Right? So that is the idea. With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing the packets. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN, okay, is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. Okay, so you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the openflow protocol. Right? So this controller here sometimes being also called the openflow controller. Just like the SDN routers, okay, some of them will actually call them the openflow routers. A scenario is this, let's send packets from H5 and H6, here and here, okay, from subnet 10.3 to H3 and H4, H3, H4, subnet 10.2, okay, but through a very specific route, okay, from S3 here through S1 and then reaching S2. So yeah, we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this, okay, if you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hub, okay, this is the shortest path. Traditional routing does not provide you the flexibility of, manually configure a specific route. But hey, luckily we have the openflow controller. So openflow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, and S2. And these entries will look like this. Okay, inside S3, the flow entry will look like this. Source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now the entry in S1, this router at the bottom, will look like this. If the ingress port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 flow entry looking like this. Ingress port being 2. Yeah, so the packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. All right, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So data go this way. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So openflow, really nice and flexible. So something to add is just here. traditional routing implements a routing algorithm. You know what? Yeah, the controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional routing. And that takes us to the first quiz today. Hey, what does these two look like? These are two more SDN flows. Okay, if you look into the content, okay, the first rule is actually saying if the IP source is 10.0.0.1 and the source port number is 52391, then take these actions. Okay, so we've seen actions that's dropping packet, that is forwarding packets. We have not yet seen modifying header fields. So these two actions are there to modify the header fields of the packet, okay, matching the source address 10.0.0.1, source port number 52391. So for these packets, we change the source address to 140.112.42.161 and the source port number to 11.999. And there's a corresponding entry in the SDN router. It says, if the destination address of the packet is 140.112.42.161, wow, coincidentally, okay, the address that we changed the packet to, the source address of the packet running through the first rule. Okay. And the destination port number, if it matches 11999, then we actually what? Change the destination IP address back to 10.0.0.1 and the port number back to 52391. Okay, so these two rules are working in a pair. Yeah, I know. Hao Yu has a question. It just popped up in the live chat. Okay, so let me finish the quiz and I'll come back to address the question. Okay, so these rules are there in this SDN router's data plane. So what do you think these two entries are for? So yeah, this should be relatively easy. So let's give it 3 minutes. All right. So in this shape, S2 has a firewall that blocks the direct sending. Oh, interesting. Okay, team 4. Team 5. I see. Yeah, I know. It's quite obvious, right? So team 4, I think Hao Yu and Kevin, both from team 4, are saying that they're for NAT. Exactly. So 10.0.0.1 is actually a very classic local fake IP address. So replacing the source IP and the source port number to something that looks more global, okay, is what the NAT is doing when they're sending packets out, okay, to the global network from the local network. The other entry then is to map, okay, in case destination address coming back in, okay, to the net box there, okay, is exactly the global IP address. And the destination port number, if it matches, okay, one of these entries in the NAT table, Okay, then we'll translate the destination IP address and the port number back according to the NAT table. Okay. So you see here, the SDN router also, okay, not just working with the remote controller using the routing algorithms to calculate the routes, okay? Not just that the network admin manually setting up entries for the firewall for security purpose. Okay, the SDN routers there also, okay, work with the NAT functionality that is also working in the remote controller. Okay, so that is yet another process you might see in the remote controller in SDN-based routing. So very good. So team 13 also came up with the entries being for NAT. Team 2 as well. Okay, good. And good morning to Kevin, Bingjia, and RNG and David. All right. And there was a question from Hao Yu asking, in the scenario I just described in the example, what if this S2 router in the middle, okay, has another entry blocking the packets coming from S3? Yeah, that's a very good question. Okay, so in earlier slides, that's actually the end of the last week. Okay, these fields we have in each flow entry is the pattern. Okay, there's also the action. There's also what else? I actually forgot exactly. Okay, there's actually one entry. Oh yeah, the accounting, right? So number of packets, number of bytes going through. Okay, there's actually one more field, the fourth field being the priority. Okay, so that priority field is not used very frequently because usually the system admin, the network admin, would try to make sure these rules do not conflict. Okay, but yeah, in some cases they do. Then we'll actually see the priority if the firewall entry is there and this forwarding entries we just set up in the example is also there. It depends on the priority of these two entries. If the security entry is higher in priority, unfortunately the traffic will be blocked. Okay, but if the firewall entry is lower in priority, then we'll pass the packet through and they will go on to S1. Okay, so usually these entries sometimes they will overlap. Having conflicts. So in those cases, there's this priority field that the network admin can set to try to break the tie. Okay. All right, so I think Rocket, okay, good to see you. Also, yeah, you are also saying it's NAT. Good. So let's move on to the second topic. Yeah. Finally, chapter 5, the routing function. So this is actually the favorite section in chapter 5 that Polly likes. Chapter 5, network layer, the control plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup. And you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it, right? The only thing the forwarding is doing just table lookup, and it's just pattern matching. But hey, we are sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really, okay, guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly trying to forward packets, okay, but it's actually simple, stupid. Intelligence is right here in the control plane. And the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, okay, for a particular source to be able to send packets to a particular destination, or to find a path so that packets belonging to a flow can flow through the network, okay, with the right amount of resources reserved. Okay, so routing algorithm there, very intelligent. Okay. So in fact, the first part of chapter 5 is going to sound a little bit like you're attending an algorithm course. So Polly will be speaking about two general routing algorithms. Okay, so they are graph algorithms. So provided a graph, okay, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided the graph, we could compute the shortest path from one arbitrary point to another point. So that is what the magic of the routing algorithms are. So these two general routing algorithms will be implemented on the internet as two routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now, these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. Okay? The control plane of each router might be communicating with the control plane of other routers, and together they complete the task of calculating routes, and in turn generating the forwarding table, and in turn install the forwarding table to the data plane, and in turn the forwarding function, okay, can be working really fast. Now, the new model of doing routing is called SDN, software-defined networking. So the one that's doing the route computation is the controller. Okay, this is also known as the what? Remote controller, because in SDN, okay, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. Okay, in fact, powerful machines somewhere remote. That's why these controllers are also called the remote controllers. Okay. And between the remote controllers, routing, okay, is being done where we generate the flow tables, and the CA, the control agent, now in the data plane, okay, that's taking in all these tables being transferred from the controller. Okay, in between, there's this openflow protocol. Okay, now you should know after chapter 4. So, after the control agent receiving the flow table, though, the flow table gets installed, and therefore the SDN routers can do, flow table lookup. Okay, do generalized forwarding. Now, the remote controller here, okay, it's actually quite general. Inside the remote controller, you could implement multiple routing algorithms, such as the one used by the traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences, or specify costs, okay, or specify other functions. Okay, so SDN's remote controller, being very general, okay, it's actually working like pretty much a regular computer, okay, or expensive servers. So on these SDN remote controller, okay, we run, okay, operating systems, elaborated operating systems, such as ODL or ONOS. Okay, so these are two different operating system architectures, and both have big camps of supporters. So SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay. So these protocols, as well as these two, okay, of the technical components in chapter 5, concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management. Okay, so management of the routers, or the routes, or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that. So that the network admin can know better the status of the routers, the status of the routes. Okay, so again, for management purpose. Let's go real fast through 5.1, the introduction. Again, network layer, we run two major functions, forwarding and routing. Forwarding is about moving packets real fast from one router to another. Routing, however, is for each router to generate this forwarding table or flow table, or to determine the routes for the packets to move, okay, from one to another router. So, in Chapter 5, we focus on the control plane here. The two models, okay, for route computation are these: the traditional routing versus the SDN routing. In the traditional routing, each router implements part of these routing algorithms, and so the route computation is somewhat distributed, and the routers work collaboratively to come up with the best routes. Okay. So there's per router control plane doing the route computation. But in SDN, okay, the route computation is more centralized, running on powerful machines, and also somewhat distant from the physical routers. So centrally controlled. And this control is called the remote controller, as they are being physically distant from the router. More specifically, in traditional routing, okay, the routing algorithm is implemented and running on each of these routers. And they'll be interacting with each other to generate the best routes, therefore coming up with the forwarding tables. Okay, so in the data plane, yeah, there's this forwarding table in the data plane. The control plane there runs the routing algorithm, and together they generate the forwarding table and forward it and installed in the data plane. Now, the modern routing, the SDN routing, works this way. Okay. There's going to be a remote controller there, okay, doing all the computation and then interacting with the local control agent to install these forwarding tables, or more precisely, flow tables. So router, yeah, data plane here, having these control agent, and then at the control plane, we have powerful machines running the remote controller. Remote controller interacting with the CA, setting up these flow tables. Now the core of Chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay, such that this path here is the least in cost, so we pay the least, or the delay is the shortest, or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay, so finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network, okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. Yeah, VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see, we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here E here stands for edge. So if you consider the routers being nodes, so the set of router here is the N here. If you consider links being the edges, then E here is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. So for example, in the application layer, chapter 2, for P2P, you see there, there are peers here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peers as a node, and these TCP connections or UDP connections connecting the peers as an edge, there, you also have a graph. You also have a P2P network. And you can also run a routing algorithm, on a P2P network, if you think about it. And now we can talk about this other thing. It's called the link cost. So associated with each link, on a graph like this, you see a number nearby. That is the link cost. To denote the cost of a link connecting router X to X prime, we use this notation, CX prime. So CWZ, connecting router W to router Z. The link here, the cost of that link is 5. Right? That cost can be set in a variety of ways. For example, set it as the inverse of the bandwidth available. You can also set it to the inverse of the traffic level. You could also set it simply to a constant, such as 1. Every link costs the same, 1. So that is link cost. Now the cost of a pass, is essentially also very simple. From the source x1 to the destination xp, it's the sum of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c, x1, x2, plus c, the first router to the second router, x2, x3, and so on and so forth until the last router, xp minus 1, to the final destination. So let me use an example. Let's say traversing from U to Z, and we take this path. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. All right. So the goal of routing algorithm is essentially to find the least cost path between a pair of nodes, from source to destination. In Poly, we'll be introducing 2 routing algorithms next. First is called the link state algorithm, second, distance vector. The link state routing works this way. Inside the network, each router, in the router, it implements an algorithm. Before this algorithm can be triggered, the router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network. E, the set of links interconnecting all these routers in the network. And link costs of all the links connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows, okay, all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths, okay, for all the possible destinations and source pairs. On the contrary, in distance vector, routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information. Namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimum results. Okay, so each router there, after running the distance vector algorithm, will know just slightly better than, nothing. And that information is definitely not quite good enough to give us the least cost paths. So what distance vector routing does is there. Each router will then, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. Okay, so if the router again discover better paths, then tell the good news to the neighbors. Similarly, neighbors would also tell slightly more information to the router. Okay, as such exchange expand, gradually traveling through the network. Okay, all the routers in the end learned about converge to the least cost path. Okay, so the process you see, computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, everyone converges to the least cost path. So a very different model of doing route computation. Link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this. By judging at how the routes are being updated. Static routing is not updating the routes. So this is only for the network that is not changing frequently. And we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way, dynamic. That is also saying that routes can change, link costs can change. Routers could suddenly be dead and then or suddenly being booted up. So we'll try to update these routes, repeat the computation periodically, or in case we detect there's a link cost change or no change, or some other changes. Now finally, the link state routing algorithm. So what's implemented there essentially is the Dijkstra's shortest path algorithm. This is very well known in graph theory. Again, as mentioned, in order for this algorithm to work, we need the global information, network topology, link cost. And this information is acquired by sending these link state broadcast messages. So each router will be sending information about itself and how it connects to other neighboring routers and what is the link cost to the neighboring routers. And that information from each router needs to be broadcast around the entire network until every router on the network receives link state broadcast report from every other router. Then all nodes will converge to the same information, same network topology, link cost, and therefore beginning to compute the least cost path. So once the computation is done, we get the forwarding table to install to the data plane. Now, something extra is this. The computation itself is iterative, okay? But it's not working iterative like the distance vector. The distance vector's iteration is computation, exchange, and computation, exchange. The computation part and the exchange part is being iterative to each other. The iterative here meant, okay, there's a loop, okay? The computation is actually working a loop, iterating through multiple loops. Therefore, okay, if we have k destinations, it takes a loops or a iterations to complete the route. Okay, so, yeah, the algorithm itself is looping within itself, but the computation will be done, okay, all at once without exchanging further information with the neighboring routers. Let me introduce these notations before I bring up the pseudocode for the Dijkstra algorithm. First is CAB. This is the cost of the link connecting router A and B. You should know already. Yeah. What's a little bit surprising to you is this. The cost CAB could be infinite, okay, because there's no direct link connecting the two routers, and therefore the cost is infinite. Second notation is this, DD. Okay, small d here is indicating that for a particular destination, the path from this router doing the computation to this destination, what is the cost of the path currently? Okay. So capital D here actually stands for distance. This is also saying what is the current distance to a particular destination D for this router doing the computation. Now, PD here, D again is the destination, okay, and PD is to indicate for this router to reach the destination D, okay, along all the routers on the path. What is the previous router before reaching D? Okay, so predecessor node along the path until reaching D. And prime is the set of nodes whose least cost is already known. So here's the pseudocode of the Dijkstra algorithm. There are two phases, the initialization phase and the looping phase. A looping phase looks really complicated, so let's not worry about that part yet and focus on the easier part, the initialization phase. So what we're doing first is to initialize the n prime, the set of nodes we know already the best route to. And we're quickly including A. The reason is this. Whenever we execute once the Dijkstra algorithm, we give also the source of the path. So A here is the source of the path we're trying to discover. In fact, after running through a Dijkstra algorithm, we will discover, okay, the shortest path to every other node in the network. Okay. Now the source, in case A is also its destination, hey, it's trivial, isn't it? We just don't send it down. Send it to 127.0.0.1, the IP address for the local host. So we can initialize n prime to just the source node safely. Second thing we do is actually a for loop here. Okay, inside the for loop, we'll go through all the nodes, okay, in the network other than the source. So all other nodes, okay, and for each node, okay, B, we check whether it's directly connected to the source. If it does, we've discovered a way to go to this particular destination, isn't it? And the distance to it is the link cost between node A and node B. Now, if the node is not adjacent to A, then it's going to trigger this line here. No route has been discovered yet to this destination B. Therefore, distance to the destination infinite. Okay. Now, from the description, you probably also see, in order to find all pair shortest path, you need to repeat the Dijkstra algorithm, providing a different source address. Okay. And that's all the time we have for this week, for today. So we'll continue and talk about the looping part, the looping phase of the Dijkstra algorithm. That is the part that's exciting. Okay, so we'll actually resume the Dijkstra algorithm tomorrow. And in the meantime, let me address Pei An's question. Yeah, is openflow a non-profit organization? It is. It's actually a political body. So there are participants there discussing, okay, how we define this protocol. Okay, so usually what they're defining are the functionalities, and for each functionality, how should the API look like? How many parameters required to call the API and then execute a function. So it's almost like defining a protocol, defining a operating system. Okay. So some of these operating systems you know are open source. Some of these programming languages you know are open source. But you also see some other programming languages, some other operating systems are being more secretive. Okay. So depending on the mentality of these companies or these member companies participating in openflow, okay, you see that argument between them. Okay, some would like these being more open source, but some of them like them being more secretive so that they can protect their intellectual property rights. Okay, so yeah, and that's all for today, and I'll see you again tomorrow. Okay, and by the way, the lecture tomorrow is going to be quite intensive. We'll be seeing the Dijkstra algorithm, that is the algorithm running in the linkstate routing. We'll be also seeing this Bellman-4 algorithm. That is the algorithm running in the distance vector routing. So the global routing versus the local routing. Okay, you'll see both of those tomorrow. And I'm gonna leave the streaming session on for just a couple more minutes, okay, in case you have further questions. And then I'll close the stream after that. And then, yeah, go get lunch. I need to go to the restroom. that's all, guys. Let me end the stream right here. You sure you want to end your